use a very simple example to demonstrate the concept of closed, right? So if we talk about the field of integers, let's say I talk about the field of positive integers. Right? So that's what this field is. It's a set, right? With respect to this particular set, what kind of operators are closed? Well, I can define a multiplication operator which takes two elements from this field and produce another element like that, and you can claim that A3 is guaranteed to be from this field. Right? No matter what are the values of A1 and A2, it guarantees that A3 is still found in the same set. Right? And same for the operator plus. But not for the operator of division. Right? So if you have this, and you define this as it's not guaranteed that output is from the same field. So using this simple example, you understand the concept of being closed, right, for operator with respect to a particular set. So what's the significance of this? Well, once you have an operator that's closed, you can compose, for example, you can compose these two together in any fashion you like. Why? Because the output of one operator is always going to be a valid input to another operator. But it is not true for the division operator. You may argue, wait a minute, I can definitely compose division and multiplication together, right? That's because in that case, you are operating in the field of real numbers, not in the field of positive integers. Does that make sense? And with respect to the field of positive integer, if you define division as that, you cannot possibly take the output of this and apply that to a multiplication operator, because if your multiplication is defined with respect to only positive integer, it wouldn't be able to understand what a real value is. Does that make sense? Right? So for relational operators, all relational operators are closed with respect to the relational model. In other words, it takes one or two relational instances as input and guarantees to produce another relational instance that can be described by the relational model. So that being said, we can take the output of the selection operator, which guarantees to be a relational instance. No matter what the input instance is, I know for sure the output is still a relational instance. And then I can take that as the input to the projection operator and build a more sophisticated query like that, which gives you the output like this. Okay? Next, we'll move on to the other two operators in relational algebra called union and set difference. These two operators, unlike the selection and projection, which we call them unary operators, because they take only one relational schema as its input. These two operators, on the other hand, are what we call binary operators, because they take two relational instances as their input. So it requires two relational schemas as its input. Furthermore, these two operators require the two input schemas to be what we call union compatible. So what do I mean by union compatible? Well, the two relational schemas, right, serving as the input to either a union or set difference operator must have the same schema. They must have the same schema in order for you to apply either the union or set difference operator. So what that means is you can take students 1 and students 2 or Sailors 1, Sailors 2, you can union that. That's okay, because the two schemas are identical. However, you cannot take a Sailor schema, union that with a boat schema. They are not union compatible because they're not even the same type of relations. Okay, that's the definition of union compatible. Any question on this? Yes.
So in other words, they have to have the same schema, the two tables?
Yes. The two schemas serving as the input to a set union or set differential operator must be identical. Okay? So to be more specific, when I say the schemas are identical, I mean the following. They must have the same number of fields, and each corresponding field from the two inputs must have the same type. Okay? So that's a formal definition of two schemas are identical. Same number of fields, and the corresponding fields must have the same type. I see some questions.
I was just going to ask, is it kind of like two methods having the same signature? Is that kind of...
Two, say again?
Is it sort of like two methods having the same signature?
Well, it's
not necessarily like the parameters can be named the same thing.
Well, it's kind of like two objects are described as the same class. I think that's a better way to understand this.
So you could take, for instance, the students, like say you have student ID and name, and then you have like Sailor ID and name.
Okay.
Can you union those two?
Excellent question. Okay. So this is an excellent question. So let me repeat so the rest of you can follow this. Based on what I said so far, it's not hard to say that we can union two different Sailor instances, Sailor 1, Sailor 2. I can clearly union these two, right? Because they have identical schemas. Sailor ID, Sailor ID, Sailor name, rating, age. What about I have a Sailor schema, simplified Sailor schema that has Sailor ID, Sailor name, only two columns, Sailor ID, Sailor name. And I have another schema and corresponding instance called student that has student ID and student name. Furthermore, let's assume in both cases student ID and Sailor ID are just integer. Student name and Sailor name are just string. You follow the setup? This question was, I understand I can union two different Sailors instances. They obviously have the same schema, so no problem. Can I union the Sailor instance with that student instance in the example I just gave you, in the setup, just give you Sailor ID, Sailor name, student ID, student name, when they have identical types? Is that your question? Okay. The answer is yes, based on this definition. As long as they are union compatible, where union compatible is defined as those two conditions. And obviously in that setup, those two conditions are met. Yes, you can union. Okay. So here is one example for set union, which basically, if I draw this using a diagram, each relational instance is nothing but a set. This is set 1, and this is set 2, right? Suppose these two sets have the same schema, What union does is to essentially take this whole thing. That's what the union does. Okay? So let me, given this particular illustration, let me ask one of you to answer the following question, which is, do you have to do duplicate elimination for a union operator? Do you have to do duplicate elimination for the output of a union operator?
Yeah.
Yes. Why?
Because you've got set 1 and set 2 both may have some of the same elements, and you don't want to have duplicates of those. So like you have set one has, say, Jared in it, and set 2 has Jared as the same person.
Yeah.
Then you're gonna have two copies of Jared. You have to eliminate one of it.
essentially you are referring to this part in the middle, right? So every element that's found here belongs to both set 1, set 2. As a result, those records will show up twice in the output of union, and they are duplicates, which is not okay for a relational model, so you have to remove duplicates for that reason. Okay? So that's for set union. Set difference. So this is union, right? What about set difference? Well, set difference is all records belong to set 1, but not from set 2. So all records belong to set 1, but not from set 2. So you take the entire set 1 and take out those records at the same time that belong to set 2. So that will be your output for the set difference operator. Okay? One immediate observation you can make is that set difference operator is not commutative, meaning you cannot swap the orders of the two inputs to a set difference operator. In other words, this is not equal to set 2 minus set 1. Why? Because set 2 minus set 1 will be this part. Obviously, they are different. But union operator is commutative. Because whether you do set 1 union set 2 or set 2 union set 2, set 1, you always get everything from the two sets. Does that make sense? Let me ask another question. Do we need to worry about duplicate elimination for this operator, for the set difference operator? You said no. Can you explain us why?
Because if set 1 doesn't have any duplicates, then set 1 minus set 2 also won't have duplicates.
Okay, what you essentially said is essentially this. And I'll prove. Right? The output of a set difference operator is a subset of the original set. And the original set is duplicate free. A subset of that must be duplicate free. So all you need to show is this. Okay? So you don't have to worry about duplicate elimination. We also have this particular part in the middle. Sometimes we want to find out this particular part. And that's what we call intersection, right? And oftentimes we do that using this operator called intersect. However, if you go back to see the setup of relational algebra, interestingly enough, we do not have the intersection operator. We do not have the intersection operator, right? So you may wonder, okay, how can I do that? If you don't give me the operator, how can I find out this part? Someone tell me how to do that?
You take the union and just subtract off the set 1 and set 2, and then you'll have the intersection.
Okay, so attempt number 1. I take the union. Okay, that's what you said. Subtract away. And subtract set 2. Is that what you said? Excuse me? Hello?
That's what he said.
Is that what you said, right? Okay. This, if you think about it, what's the output? Okay, let's walk through this, right? Union gives you this. Then I subtract away set 1, so everything here is gone. And subtract set 2. This is no longer part of. This part is no longer there. And when you subtract set 2, then this part is gone. What you end up with is an empty set. It's wrong. Okay?
I think I have a better solution.
Okay.
So set 1 union set 2 minus.
Hold on. Let me. attempt number 2. Set 1 union.
Set two.
Okay.
Minus, open parentheses,
Minus what?
minus in parentheses, set one minus set two. Minus set two minus set one.
Okay. All right. Looks complicated. Okay, let's try to work out the math. So this gives you the whole thing, right? This entire thing. And set 1 minus set 2 is this part. So when you subtract away that, what this gives you is, essentially this essentially equal to set 2. Right? Does that make sense? Because you're taking the whole thing minus with this part, that gives you essentially this part. So it doesn't have to be this complicated, first of all. Okay? So what you said is essentially this. Is this right? Now this works, right? Because set 2 minus set 1 is this part. And you use set 2 minus that gives you this part. Oh, sorry. Set 2 minus set 1 is this part. And you use set 2 minus this, that gives you exactly the intersection part. So it's right, but it doesn't have to be that complicated. And similarly, another way of doing it, you do this from the set 2 point of view. You can do this from set 1 point of view as well. You can do right? That's another way to do this. That's another way to do this. And that explains why we do not include intersection in one of the basic operators in relational algebra, because you don't really need it. You can express the operator using the combination of other operators. Does that make sense? Okay. One final remark I'd like to make right here is set operators are not like your algebraic operators. In other words, you cannot take this and simplify like math, like algebraic math. Like say, oh, this is equal to set 1 minus set 1 plus set 2, and is equal to set 2. No, you cannot do that, okay? It's not algebraic math. All right, so those are some very basic concepts, okay? So we know how to express intersection now, okay? Now, cross product. The last operator in relational algebra is this cross product. Again, it's a binary operator. It takes two, excuse me, it takes two schemas as input and produce a single schema as its output, where the output schema, let's first define the output schema, then we define the output instance, okay? The output schema is the union of the two input schemas. Meaning you take every attribute from the first input schema and take every attribute from the second schema, put them together. That's your output schema. And the two input schemas do not have to be union compatible. They can be anything. Like students cross with sailors, student cross with boats, boats cross with sailors. You can do all of this. That's the output schema. Does that make sense? What about the output instance? Well, the output instance consists of all the possible pairings between every record from the first input instance and every record from the second instance. So that's the definition for the output instance. In other words, you take the first record from the first input instance, pair that with every single record from the second input instance. Then you move on to the second record of the first instance and do the same thing. So at the end of the day, if you have n records from the first instance, m records from the second instance, you end up with n times m number of records in the output. Okay? So for example, the output of this will be these 6 records. The first sailor record pair with every single graduation record, and so on and so forth. Okay? That's the cross product. So whenever you use cross product, it's useful to use another operator. It's not a relational operator. It's really just a kind of like a utility function kind of thing, right? It's not a relational operator itself. It's more like a utility function. Whenever you do cross product, you might have to use this utility function called renaming operator, which is written as the Greek letter rho. So a renaming operator works like the following. It takes two parts. The second part is your relational query. Okay? Any relational query. Any relational query, that's your second part. The first part, try to redefine the schema okay? You try to redefine the names for certain fields in the output schema. Okay? What's the output schema? Output schema is defined by this relational query vector. And this is where I have to go back to a point I skipped earlier, purposely, because I don't want to confuse you then. But now we have to use that particular concept, which is this positional versus name field notation. So far, in our discussion, whenever we try to refer to a single attribute or a set of attributes from a schema, we always use the name of the attribute to rename to that particular field, right? Students.name, student.rating, or sailors.rating, sailors.age. Does that make sense? Right? Like if you look at the projection, sailor name, rating. If you look at the selection, rating, so on and so forth. We've always been using names of a particular field or a set of fields to refer back to those columns from a schema. Another convention you can use to refer to one or more attributes or fields from a schema is by its position, by its positional index. What do I mean by that? Sailor ID, that's clear, right? Sailors.sailor ID, that refers to the sailor ID column from the sailors schema. You can also do sailors.1, that refers to the first attribute from the sailors schema, which is still sailor ID. That's what we call positional notation. Is that clear? Fairly straightforward, right? So using this notation, now we can do this. We can do this renaming operator. For example, what this means is I take the output schema, which is the cross product between S1 and R1. I rename the whole thing to a schema called C. So subsequently, whenever I refer to the schema C, I know is basically equal to this. Once you have done this, then subsequently you know C is essentially this. Furthermore, not only you can rename the name of the output schema, you can also rename any field in the output schema. For example, when I do this, what does it mean? 1 to SID1 and 5 to SID2. That means from the output schema, the first attribute will be renamed into an attribute called SID1, and the fifth attribute will be renamed to an attribute called SID2. You have to do this for this particular cross product because you have two SID fields in the output. And if you do not rename them, they're going to cause ambiguity in the definition of the output schema. So if you look at the output schema is all the attributes from series plus all the attributes from the reserved table. Okay? Clearly, you have two SID columns, and if you don't do nothing about them, they will cause ambiguity. Now rename them. One become SID1, and the fifth become SID2. So this will become SID1, and this will become SID2. What about those attributes that do not appear in the renaming operator? Well, they inherit whatever the original name they have in the output schema. So they say no change. Procedure name, reading age, be at the end, they stay the same. The name of those attributes stay the same. Okay, that's the renaming operator. Any question on this?
Is the index always one base, or is it sometimes zero base?
It's in our convention, we're gonna use one base. Okay. That's it. Those are the 5 basic operators in relational algebra. Looks fairly straightforward, right? But using those 5 basic operators, you can do a lot of powerful things. I'm going to show you some examples next. The first example is intersection. We talked about this already, so I'm going to skip this. By the way, for intersection operator, you do not have to worry about duplicate elimination. Why? Sorry, you do have to worry about duplicate elimination. Why? Because intersection is to find the common records that appear in both set 1 and set 2. In other words, they will appear multiple times, so you have to remove duplicates from the output of an intersection operator. Okay. Now excuse me. Another example of what we call the compound operator. By the way, compound operator means that it is not one of the 5 basic operators, but can be expressed using the combination of those basic operators. Okay, using the combination of those basic operators. So another really useful operator that's not one of the basic operators, but can be expressed using a pipeline of basic operators is the join operator. And in particular, we're going to start with this thing called natural join. Natural join is written as this, R natural join S. So it takes 2 schemas as its input. And what it produces is the following. So I'm going to define natural join first. Then I will explain to you what's going on, okay, and see whether you can understand the definition of it. Yes?
Before you move on, I think what you were saying, intersection of 2 sets should not have duplicates because it's
intersection of 2 sets should not have. Why?
For example,
The intersection is exactly this part.
Yeah, it's a subset of one of the sets.
Well, of course, it should not have duplicates, but that's because you have to worry about eliminating the duplicates. You are finding all the elements belong to A and B, right? So from the first set and second set, both will give you a copy of that same record.
Yeah, I can use a similar proof you did earlier. It's a subset of set A. And the set A doesn't have.
Yeah, it depends on how you implement this. That's what I'm saying, right? So
okay, all right.
Conceptually, yes, it must have no duplicates, but you have to worry about removing duplicates. All right. So natural join R, natural join S. What does it mean? Okay, I'm gonna express this using. First of all, it's R cross S. Okay, you find the cross product. Okay, now you're going to purge that out. Okay, hold on. And then you do a selection. The selection will be okay, will be this where if a common attribute appears in both R and S. Okay? AI is a common attribute appearing in both R and S. For example, if student schema has an attribute, so student might not be a good example. Let me use the example we have, reserve and sailors. If you look at this example, okay, what are the common attributes between sailors and reserve? There's only one common attribute, which is sailor ID. Does that make sense? What is the common attribute between both and reserves? Boat ID. What are the common attributes between boat and sailors? No, they do not have common attributes. Does that make sense? So for every such common attribute, you enforce equality condition on that common attribute from the output of the cross product. And you select out those records. Okay? And finally, you do a projection. You project out everything from the schema of R cross S. So take everything, but for common attributes, you project out them only once. Because if you have R1 in both R and S, you're going to have two copies of A1 in the output schema of R cross S, right? Because somewhere you're going to have A1 here, somewhere you're going to have A1 here. So in the output schema, A1 will appear twice. And what the projection does is to keep all the other attributes, take all of them, but for the common attributes, take only one copy of them. Make a lot of sense because you enforce them to be equal. Why you want to take the same value twice when you know they're guaranteed to be equal after the selection condition? Okay? Take only one copy of these AIs, where AI refers to those common attributes. So that's the definition of natural join. Okay? With that definition, I'm going to show you a specific example how this works. So here is the example of natural join. Serial 1 join with reserve 1. First of all, it will produce the the cross product of the two, which is, we just saw that a couple of slides before. So that's this. And from this, we look at common attributes. What are the common attributes? These two are the common attributes. And we do that selection, which is CID equals to CID. So this will survive. This will be eliminated. This will be eliminated. This will be eliminated. This will be eliminated. And this will be eliminated. Sorry, CID out. So I'm looking at CID. So this will survive that selection operator. This will be eliminated. This will be eliminated. This as well. This as well. But this will survive because the CID are the same. So this one and this one, these two records from the cross product satisfy that selection condition on common attribute, which is CID in this case. That make sense? And then finally you do projection. What do you project out? You project out everything, which is this, 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 and this, and this, and one copy of the common attribute. So for these two CID, you take one of them. Doesn't matter which one you take because they are guaranteed to have the same value. So the output schema will be CID, serial name, rating age, boat ID, and date. That's the output schema. Everything except only one copy for the common attributes. And the output instance will be this and this, but only one copy of the common attributes, so this will be gone. So what you end up with is that. Okay? Any question on this? So that's the natural join operator, okay? We have other type of join, right? Sometimes you do not want to do just equality join on common attributes. You might want to use some other type of join conditions. Or you want to do equality join, but you do not want to force equality condition on all common attributes. You want to enforce equality condition on only a subset of common attributes. For either of those cases, natural join will not do the work for you. Does that make sense? Natural join will not do the work for you. So we have to introduce another type of join, which is what we call theta join, or condition join. Right here, I guess. This is known as condition join, or simply theta join. They both refer to the same thing. Where C is a Boolean expression over attributes in R and S. So now condition C is defined using some attributes from R and S. So this is actually much easier to understand than natural join. All it does is the following. You cross product first, and you do a selection using attribute C over the cross product. That's it.
So by conditional, do you mean like you would check, for example, you would say only give me the tuple for people who got a rating above 8, or something like that?
Yeah, that's one example.
Okay.
But oftentimes the condition involves attributes from both R and S because you are trying to glue them together. Of course, you can enforce the condition on only one of them. That's essentially doing the cross product check condition only on one of them. But oftentimes you do things like this. That make sense? So this is the one example of condition join. So what you do is you take the cross product, which is this whole thing, and you check Sailor ID must less than reserve Sailor ID, right? Is that the condition I'm using here? Yeah, Sailor ID must less than reserve Sailor ID. So what do you get? Well, is the Sailor ID less than reserve Sailor ID? No. Is the Sailor ID less than reserve Sailor ID? Yes. So this will be in your output. No? 31? 22? No. Yes. No? No. So this two will be your output. Okay? Sailor ID less than reserve Sailor ID. Sailor ID less than reserve Sailor ID. Only those two records satisfy you theta condition, the C over there. And note that there's a distinct difference between condition join and natural join. What is that? There's no projection for a theta join. Does that make sense? In other words, a special case the special case here is C is equality condition on all common attributes. Does that make sense? In that case, can we claim this is the same as natural join? Yes or no? Does that make sense? What I'm saying? You condition C, for example, you condition C is essentially R1.A1 equal to S.A1 and R.A2 equals to S.A2 and so on and so forth. For all those attributes appear in natural join, right? Are they the same? Now are they the same? Well, just look at the definition. They're still not the same. Why? Because there's no projection at the end, meaning a theta join always keeps all attributes from the cross product. Whereas natural join keep everything, all attribute from the cross product, but remove one copy of common attributes. In other words, if you were to do equality condition on all common attributes for S1 and R1, in other words, you do theta 1 join with reserved 1, where theta 1 dot theta ID versus theta 1 simply natural join R1. What are the difference? Well, they are almost the same, except that the output of this has 2 SID columns. The output of this only has 1 SID column. Otherwise, they are identical.
What about the number of instances?
Sorry?
What about the number of instances? Are they? Do they
Number. You only have 1 instance.
Oh.
You always have only 1 instance. What you're saying, number of records in it. Well, they guarantee to have same number of records, obviously, because projection never remove records. Projection remove columns, right? Obviously, they're gonna have same number of records. Okay. Okay, so far these are simple examples, right? The next one I'm gonna give you is a little bit more involved. The join, the intersection, these are fairly easy to understand, right? The next one is a little bit trickier to understand, okay? So do pay attention and try to follow the discussion here. The next operator is called the division operator. By the way, inside a relational database, when you coughing is killing me. So the join, this is only a conceptual way to understand what's going on for a join operator. Inside a database system, you never do any join using this approach. Meaning you do the cross product first, then you apply the condition one by one, then do projection if needed for natural join. Why you never do this? Because if R has n records, S has n records, this is n squared cost. You cannot afford to do that. Right? We can afford to do that for our class database. Google cannot afford to do that for their database, right? If Google start doing this, your Google search will never return, obviously, right? N squared, right? So for a million record, I think I showed that calculation before, right? For a million records, if you do a join over them, that's 10 to the power 12. And that will take forever. Right? So inside inside a database system, you never carry out a join like that. And in fact, this actually helps you to understand a statement I made at the beginning of the relational algebra discussion, which is relational algebra is more operational. What do I mean by that? If you look at a relational algebra query, right? Let's just look at this. It's very operational, right? If anyone look at this, you say, oh, I will do the cross product first, then I will do the selection condition. So in some sense, not only you are specifying what you want, you are specifying how to do it. Very operational. Not only I tell you, oh, you need to fly to Boston tomorrow. That's like me telling you. Versus, oh, you need to fly to Boston, pack your clothes, book the 8 a.m. flight, make sure call your uncle when you land. That's your mom telling you. Right? So it's very operational versus what to do versus how to do. Right? Operational in that sense. Right? Relational algebra is very operational. For that reason, inside a relational database system, what the system will do is take the SQL query as input, and the first thing it does is translate that SQL query into a relational algebra representation, so that it represents not only what to do, but as well as how to do it. That translation, okay, from SQL to relational algebra, for now we just view that as a black box. Does that make sense? And for the undergrad version of database class, I'm not able to go too much into the detail of that black box, because that black box is really all the magic that's taking place. That's why Oracle is making more money than some other database company, because they can build a better magic black box than other companies. Right? For example, if you know nothing about database, you may implement a database system where the black box is, oh, John, I want to do cross product, then do this. Your database will never sell a single copy because no one is going to use your database. Yes, it's right, it does its job, but it's too slow. Nobody's going to use it. Oracle has a black box that does this much better. So it will take the join and translate into something else. Right? And that translation is non-trivial. Coming back to the discussion here, the division operator. Okay, so the division operator, again, what I will do is I will define it first. And then go over the slides with you together. So the division operator is written as A divided by B, where A and B are two input schemas. So first of all, let me define the instance of the output. Okay, I think one thing. Okay. Once I define the instance of the output, the schema of the output becomes clear as well. Remember, always there are two things. For any relational query, you want to ask two questions. One is, what's the schema of the output? And then secondly, what's the instance of the output? Typically, we go with defining the schema of the output first, then defining the instance of the output. But in this particular case, I'm going to do a reverse, which is I'm going to introduce you the instance of the output first. Then from the instance of the output, we will infer the schema of the output. So that's what we will do. So what's the instance of the output? Clearly, it must be a set, because it's a relational model. An instance is just a set of records, so it must be a set. That's rule number one, right? Without even looking at this, I know it must be a set. What goes into that set? Well, if all such x, okay, where for any y belong to B, so B refers to an instance of B, okay? B is the instance. I'm building the notation so a little bit. B referred to both the schema and its instance, okay? Is that okay? Depending on the context. So B referred to either the schema or the instance of that schema, depending on the context. Here I'm using B as the instance of that. Okay? That make sense? So for any record from Y, any means for any. Okay? There must exist a pair X and Y from A. That's it. That's the definition of division. So you're trying to find all these X such that for any Y, XY must appear in A at least once. See a lot of puzzle face? Let me show you using an example. First of all, if you have trouble in understanding this, you should have no trouble in inferring out the schema of the output. What's the schema of the output? What is the schema of the output? By this definition, the schema of output must be able to describe this X, which is all the attributes in A, but not in B. All the attributes in A, but not in B. Why? Because for any X matched with Y belongs to A, which means the schema of this whole thing is A, and this part, the schema of Y is B, so the schema of X must be all the attributes in A, but not in B. Right? Okay, so the schema is clearly defined. What exactly it does? Well, let's look at this example. Suppose I have a very simple schema. Student number and product number. It tells you, this table tells you who works on which product. This is how to understand. Student 1 works on product 1 to 3, student 2 works on product 1, 2, and student 3 works on product 2, student 4 works on product 2 and 4. Right? Very typical, simple database. For this very simple table, I want to answer the following, which is, who works on product number 2? Well, you argue, okay, I can do that using a selection. I can select from A where product number equals to product number 2. Right? That's one way of doing it. The other way of doing that is to do division. I use A divided by B1, where B1 has only a single product number, which is B2. Before I show you an answer, let's come back and look at the definition. So in this case, this becomes B1, right? Because that's my instance. It's still it's an instance from the schema B. Schema B is this product number, right? Any Y from B1, any record in B1. How many records you have in B1? Only one record. Does that make sense? Which is P2. So for P2, there must exist a record XP2 from A. That's what it says. Right? You follow me? What is the X? S can be S1, obviously. S can be S2. S can be S3. S can be S4. Does that make sense? Yeah? So the output of A divided by B1 is going to be S1, S2, S3, and S4. Because if you substitute any one of them from this to this X, it's true. This statement is true. S1, P2 belongs to A, S2, P2 belongs to A, S3, P2 belongs to A, S4, P2 belongs to A. Let me finish, then I will take questions. Okay. What about A divided by B2? Well, I would do the same thing. Okay. What about A divided by B2? Now B2 now has two records, P2 and P4, right? For P2, this X can be what? For P2, X can be still all four of them, because these all exist. The pair always exists in A. S1, P2 exists in A, so on and so forth. But the condition is for all Y belongs to B2. You cannot just check P2. You have to check for P4. The same X must exist in A. Now X can be S1 is still okay. The S1 P4 is from A. What about S2? No, it's no longer okay. Because S2 and P4, this pair does not appear in the original schema, original instance of A. So S1, not S2. What about S3? No. What about S4?
Yes.
Yes. So for P4, you find S1 and S4. For P2, you got this guys. For P4, you got this guys. The intersection of them give you S1 and S4, which means for S1 and S4, they match with every single record in B. This gives you what? All students who work on both product 2 and product 4. Okay? If you follow my discussion for it's very easy to understand the last one. Who works on product 1, 2, and 4? Well, you basically use the same logic, right? You build onto this, you add. Now this becomes. So in addition to this, you have to do for P 1, you find this x, which is, we'll work on P1. x1, is that the only guy? Yeah, that's the only guy. That make sense? So which x enable this statement to be true? Meaning there exists a pair of x P4, x P2, and x P1 only if x equal to P, x1. So the output will be x1. You may argue, okay, fine, I got it. But what about if I just do this using selection operator? This is to say I select from, by the way, how do you do this using selection operator? In this particular example, I want to find student number who work on project 1, 2, 4, using, not using division, using some other operator. How do you do this? Can someone help? How do you do this? Yeah? Go ahead. Yeah.
I'm not sure I know exactly how to do it, but it's supposed to be selection, put a conditional on the P number.
Yes, you definitely need to involve a selection condition on P number, but how you construct that selection condition and how you do this. Anyone? Do you help? I want to be a little bit more specific. Yes, go ahead.
Can you do nested selection?
Define nested.
Like you select where it equals P4, and then you select from that where it equals P2.
Okay, so what you're saying is select from A where product number equal to P4. Is that what you're saying?
Yeah, and then you select on
And that from this product number equal to P2. And select from this where, okay, very good. And are you done? Is this the same as the output we have from A divided by B? Is this the same as A divided by B3?
You have to do a projection.
Excellent. You have to do a projection. Selection does not change the schema. So the whole thing, the schema is still A, which means it has select student number and product number. That'll do. Okay, excellent. That's one way of doing it. What's the other way of doing this? Right? Another way of doing it. So you may argue, let me state what I want to say then. Question. Okay, you may argue, I like this, only selection projection. I don't want to understand projection, division. If you try to do that in the midterm test, I will give you two problems. One is this. The other is I will give you a table with 1,000 project numbers and ask you to find students who work on all projects. You may argue who can work on 1,000. That doesn't make sense, right? What about manufacturing database? I want you to find companies who purchase all these parts. That can be, there could be 10,000 parts going to an iPhone, right? Does it make sense? I want to, on the right-hand side is a list of products, on the right-hand side is a list of parts. I want you to find all the final product that use all the parts. Does that make sense? If you try to do that using the selection approach, you have to write thousands of selection conditions to express that versus just do this. You follow me? So the answer is you cannot rely on this approach to express division operators. You cannot. Yeah? Question there?
For the syntax for these conditions, are you able to use Boolean
for the selection?
Yeah, so
Yeah, of course.
First example, you said P number equals P1 and P number equals P2.
Yes, that's what we said earlier. For any selection condition here, is any Boolean expression. Any Boolean expression. Okay? Any Boolean expression is okay. Question over there?
Yeah, just out of curiosity, do
Yeah.
those database systems compile back to division when you do a select statement like that?
Oh, what you're asking is how a division is actually carried out in a database system?
Yeah, so I mean, I guess how sophisticated the compiler is varies from database system to database system. But at the end of the day, does it usually take a complex selection
So
like that?
what you're asking is, yes, it's impossible for a human to write division like that when you have many records in B3. But if the database is doing essentially the same thing under the hood, the answer is no, they don't do that.
I'm talking about the other way.
I see.
So if you have a
If you're writing something like this, can somebody convert that back to division? The answer is no, because the instance of B3 might change. I may add another project number to B3. For example, I can make B3 at the moment equal to P1, P2, and P4. And when this is the case, these two are equivalent. That's another reason why you cannot use this approach to substitute division. Somebody later decides to, okay, I'm going to add P3 to B3. Do you need to update this word? No. It still gives you the person who worked on all projects from B3. But now they are no longer the same. You have to add one more term here to reflect the newly added record to B3. Does that make sense? So from a compiler point of view, these two are not equivalent. On this particular instance, they are equivalent. But if you take the bigger picture, look at the schema, the semantic from the schema, they are not the same for that reason. But excellent question. Okay? Okay, cool. But he actually bring up an interesting point, or our discussion actually leads to this, which is, okay, so I cannot express division using this. So why division is not a basic operator in my relational algebra? In other words, can we express division using these guys? Oh, before I proceed, right? One implicit requirement for you to do A divided by B is what? Is the schema must be part of schema of A. Why? Because if that's not the case, if the schema of B is not part of the schema of A, this will never be true. Right? If the schema of Y is not even part of A, meaning there are some attributes in Y never appear in A, how can this be true? This never will be true. There will be never such x, y belong to A, because Y has attributes that's not even from A. For example, sailors divide by boats. Right? Sailor divided by boats. Can you find any x such as x and all the attributes from boat is part of the sailors? No way, because sailor doesn't even have attribute boat ID, boat name, and color. How can you find such x, y from A? Impossible. When y has boat name, color, or any of those attributes. Does that make sense? So the attribute of B, all of them must be part of attribute of A in order for this to work. Okay? Question from there.
So is that operation illegal, or does it just return?
It just return none. Okay. It's not illegal by definition. It's okay. You are trying to find x and y belong to A. When y is not part of A, this is still fine, but it simply implies there are no such x. Can you find a flight from Earth to Mars? Valid question. No. A valid question, yes. Is there a flight like that? Not until now. Maybe in the future, I don't know. But based on this definition, no. Right? Now, back to maybe I will do this way. Okay, maybe I will try to. Okay, I will. Okay, go ahead and give you the expression of the division. So what about? So that means that the output schema of A divided by B is those attributes in A but not in B. Okay, that's clearly reflected from our discussion so far. The next thing is, can you express division using basic operators? Using selection, production, cross, union, and difference. Okay, that's what I'm going to do next. Okay, so what I will do is, looks like this is like almost impossible, right? How can you use those guys to express division? The way you do this is as follows, okay? First of all, you project out all, I will express A as the schema of A. I will express that as X and B. Is that okay? I will basically take all the attributes from A and view them as B and some other additional attributes called X. Okay, schema of A, and I view like that. That being said, I will do this. I will project out all such X. Remember, this removes duplicates on X. X is not necessarily a single attribute, it could be multiple of them. And what I do, I cross that with everything from B. What does this give me? It gives me all the possible pairs, all the possible matchings of pairs from all such X and every Y. But not all of them going to appear in my A. Does that make sense? Right? Yes or no? So the schema of this, by the way, the schema of this operation is A. Why? Because I take the schema of this, project out this part. So the schema of this is X, the schema of this B, cross product, put them together. So the schema is back to A. But the instance is not. Okay? What's the instance of this? Well, this is, it gives you all the X, Y's, such that X from A and Y from B. So that's the instance of this. It gives you all possible pairs. Let me finish and then I'll take your question. Is that right? Okay? So far so good? And if you use this, subtract away from A itself, what does it give you? What does it give you? It gives you those X that pair with some Y do not appear in A itself. Because these are all the possible pairs. You minus away A itself. It gives you those X that pair with at least one Y that do not appear in A itself. Further out those X, those are what we call disqualified X, because they match with at least one Y from B, but not in the original A. So you take all the X from A again, minus away them, that's what you want. Those are the x who pair with all the y's. Another way you understand, the way you understand this is, if an x from A does pair with all the y's in the ordinal A, the subtraction will take all of them out. All of those guys will be part of this. Does that make sense? Okay. So that's what we want. Okay, that's what we want. It does take some effort to understand this, but this course, let me emphasize this, right? So this is not a very difficult class, but at the same time, it's not like that easy, right? So you do have to spend some time to review after each lecture to try to understand what's going on here. Right? So let me repeat what's going on here one more time. This gives you all the x from A. Actually, let me use the running example to demonstrate this. So what I'm going to do is, I'm going to use this running example. I'm going to show how A divided by B3 works. Okay? First step, I project out this. X in our example is what? It's simply a Taylor number. Because A is Taylor number and B is product number in this case. So my X is simply Taylor number. So product of Taylor number, which is, what's the output of this? Can someone tell me what's the output of this? If you have trouble in answering this, you're going to have big trouble in midterm tests. Okay? What's the output of this?
It's the column
So tell me the specific values.
S1, S2, S3.
Yes. Removing duplicates, that's what you get. Now this cross with B, what do you get? D3 in our example, what do you get? Oh, what do I get? It's too much. I will write E2. Cross with that will give you right? That's what I get. All the possible pairs between X and Y. Minus from A, which is A is what? All of that. I'm not going to repeat myself. All of those. Now what do you get after this subtraction? S1, P2 is in A, so this will be eliminated. S1, P4 is in A. Is that in A? Yes. Eliminated. S2, P2, is that in A? Yes. S2, P4? S3, P2? S3, P4? S4, P2? Yes. S4, P4. So what do you got? You got S2, P4, and S3, P4. See how this works? This gives you those X that match with at least one Y that do not appear in the ordinal A. You put the X out of this, what do you get? These are the X who do not match with at least one Y from B. Because of that, they should not be part of your division. And then you take the whole thing, subtract with these guys, you got what you want. Okay? Now let me do some exercise. Okay? Our time is running out. I guess I will stop right here. I will continue on Monday.